Hi, my name is Kwangmin Kim from Seoul National University. I'm going to talk about optimal estimation of gasoline LP-EGR via unscented Kalman filtering with mixed physics-based data-driven components modeling. Exhaust gas recirculation is an automotive technology that adds some exhaust gas to the fresh air. For gasoline engines, it is introduced to suppress knocking tendency, thus to achieve better torque and better fuel economy. Low pressure EGR is one of the representative configurations of this EGR. As in this figure, the exhaust gas near the tailpipe is recirculated into the very upstream. This LP-EGR is typically considered more effective than other configurations because of its lower temperature at the intake manifold. However, it is challenging to accurately control the amount of EGR in this LP-EGR system. This is because the modeling is typically inaccurate with real-time runnable model complexity. For example, the orification is inaccurate due to low pressure. To enforce robustness against such modeling inaccuracies, feedback control can be adopted, which requires output and state values. For example, the O2 mass fractions at the intake manifold and the EGR flow rate at the valve. Adding some sensors to directly real-time measure these variables in production cars is generally infeasible in terms of cost, robustness, and form factor. For example, oxygen concentration sensor for the intake manifold is very expensive. Therefore, it is important to develop virtual sensors for them. The practical contribution of this paper is that we develop virtual sensors for gasoline LP-EGR. The theoretical contribution of this paper is that we propose a novel framework of optimal state estimation that efficiently utilizes multilayer perceptrons, which is applicable to other configurations or other systems as well. More precisely, we first propose a mixed physics-based data-driven modeling approach, which is more accurate than physics-based modeling, while also faster than data-driven modeling. Second, we extend the unscented Kalman filtering theory to the new nonlinear uncertainty structure that comes from the proposed modeling approach. By doing this, we optimally combine the models and the sensors with their modeling and sensing uncertainties properly addressed in the sense of UKF. Thus, obtain optimal state estimation. Third, we analyze the computational load of the proposed modeling and estimation framework. Finally, we experiment the virtual sensors for the LP-EGR, implemented by the proposed framework. The related works can be summarized by three categories. The first one is based on physics-based modeling, which is inaccurate in our gasoline LP-EGR system. The second one is based on fully data-driven modeling, whose computational load is very high, thus neither affordable to their ECU nor to their PC. Moreover, this does not consider the modeling uncertainties, thus not so optimal in the stochastic point of view. The last one is based on data-driven modeling with its modeling uncertainty considered in the extended Kalman filtering. This, however, is less robust than UKF for highly nonlinear systems. For example, it easily diverges on our LP-EGR system. We now explain the proposed methods. Let me start with the modeling. For modeling, we decompose the system into subcomponents, as in this figure. And we opportunistically apply physics-based or data-driven modeling for each component, depending on their model complexity. For the data-driven modeling, we utilize multi-layer perceptrons, which is known to be able to approximate fairly rich class of functions. More precisely, we model all the volumes using their physics, since they possess rather simple dynamics, allowing for simple and accurate physics-based modeling. By doing so, we obtain the physics-based part of the estimation model. On the other hand, the valve components, such as EGR, throttle, cylinder, do not subsume such simple and accurate physics-based models. So, we apply data-driven modeling for them. In this figure, we see data-driven modeling errors, which are prone in practice. For these data-driven modeling errors, we model their variance as a function of the states. By doing so, we obtain the data-driven part of the estimation model with the variance model of the data-driven modeling errors. So far, we have physics-based modeled part and the data-driven modeled part. By substituting the data-driven part into the physics-based part, we finally obtain the following estimation model. Now, for optimal estimation, let's focus on the structure of this model. First, both the state propagation and the measurement model are nonlinear and contain uncertainties inside their nonlinear functions. More precisely, the same data-driven modeling uncertainty is inside the state propagation model as well as the measurement model. Second, the variance of this uncertainty is state-dependent. Therefore, we have a new nonlinear uncertainty structure for UKF. Thus, need to extend the standard UKF theory to this new structure. We need to define sigma points to capture the nonlinear probability distortions of these state and uncertainties. So, we define the augmented state vector consisting of the state and the non-additive uncertainties. In order to generate sigma points, we need mean and covariance of the augmented state vector at time k. The state and the sensing and modeling uncertainties at time k are contained in the measurement at time k. Thus, cross-correlated each other given the measurement zk. This implies that they should be updated together in the Kalman correction stage of time k. Therefore, we define xb consisting of these cross-correlated variables, and then formulate the mean and the covariance of xa. Note that before we compute the state of time k plus 1, xk plus 1, we cannot compute the state-dependent variance of modeling uncertainty qmk plus 1. Thus, cannot compute the covariance Pa at time k. For this, we first compute the sigma points of xb at time k using the block diagonal structure of the sigma points formula. By propagating the sigma points of xb at time k, we can compute the state of time k plus 1, xk plus 1. From this, we can compute the state-dependent variance of modeling uncertainty at time k plus 1, qm k plus 1, and then its sigma points. Now, we have all the sigma points needed for the prediction stage. Here is the computation algorithm of the proposed UKF extension. We conduct a formal analysis on computational load of our proposed framework. Because the proposed mixed physics-based data-driven modeling consists of smaller split MLPs, it has less computation than the case of fully data-driven large MLP. Therefore, the proposed framework renders the estimator run much faster than the fully data-driven case. For example, it is 4 times faster for our LP-EGR system. We validate the proposed modeling and estimation framework through the experiment on our LP-EGR system. We implemented virtual sensors and then tested through an aggressive transient operation. In the plot, we can see the proposed estimation framework is accurate and stable. Note that it is more robust than typical extended Kalman filtering, which easily diverges in experiment. In conclusion, we propose a novel framework of optimal state estimation that efficiently utilizes multi-layer perceptrons. By doing so, we implement virtual sensors for gasoline LP-EGR. Real sensors for them too expensive to deploy in production cars. The mixed physics-based data-driven modeling is more accurate than physics-based modeling, while also faster than fully data-driven modeling. The unscented Kalman filtering theory extension to the new nonlinear noise structure renders the optimal estimation. With sensing and modeling uncertainties of the proposed model, we formally analyze the computational load of the proposed modeling and estimation framework. In experiment, the proposed modeling and estimation framework is accurate and robust in the aggressive experiment, with only production sensor setup and spec. Thank you for listening, and I hope to see you at paper discussion.